Welcome to the last in a series on the chemical bond. Specifically, we've been looking at molecules that are covalently bonded, where a covalent bond is formed by sharing all valence electrons with 2 electrons per bond, and the purpose is to achieve a noble gas electron configuration. The valence electrons are easily found through the periodic table for each element by looking at the group number. Similarly, bonding is determined by the periodic table. As the noble gases are group 8, the number of bonds any element can form is simply going to be 8 minus that element's group number. We've seen previously how to draw a Lewis structure to determine what a covalently bound molecule looks like, how to use that structure to determine the shape and the polarity, and hence the reactivity of the molecule. In this final video, we'll go into the details. Exactly how covalent bonds are formed. How can atoms share electrons with other atoms? Start with an example. Simple molecule again, methane. To draw the Lewis structure, carbon has 4 valence electrons. Each hydrogen gives 1. Having a total of 8 electrons, carbon in group 4 can form 4 bonds with a hydrogen on the end of each bond, and those 4 bonds take care of all 8 of the electrons. Now, knowing what we know about the geometry of the molecule, a bond is 2 shared electrons, which means one electron is given by the hydrogen and 1 electron is given by the carbon to form each bond. This implies, in order to form 4 bonds, carbon requires 4 unpaired electrons. Going back to the periodic table, carbon has an electron configuration of helium 2s2, 2p2. From this, it can be seen carbon only has 2 unpaired electrons. Therefore, how can it form 4 bonds? The answer lies in looking at the orbital structure. Carbon has 4 orbitals, and it also has 4 electrons. These orbitals, to form a molecular bond, are hybridized. They're essentially mixed. The s orbital goes up slightly higher in energy, and each of the p orbitals drops slightly in energy. You now have 4 orbitals of the same energy, and you have 4 electrons to distribute to those orbitals. So now, in this hybridized form, carbon has 4 unpaired electrons that it can share. This is called an sp3 hybrid because I took 1 s orbit and 3 p orbits. In all cases, when making a bond, atomic orbitals combine to form molecular orbitals in a 1-to-1 ratio. You can easily determine the hybridization with Lewis structures. Knowing that there's 1 molecular orbital for 1 atomic orbital, and knowing that there's an electron pair in each molecular orbital. If I look once again at CH4, with its 8 valence electrons, and carbon with its 4 bonds, using those 8 electrons up, is going to have the general form AX4, which means we know, first of all, it's tetrahedral. Also, Since it is completely symmetric with a hydrogen on each end of each bond, we know it's nonpolar. The clue as to how many molecular orbitals I need is in the naming. It is AX4, which means that you need 4 molecular orbitals from 4 atomic orbitals. At this point, for review, the atomic orbitals come from the quantum numbers. If L is S, m sub L can only be 0, meaning there's a single s orbit. For L is 1, m sub L goes from -1 to +1, which means there are 3 p orbits. L is 2, m sub L goes from -2 to +2, leading to 5 d orbitals. And L is 3 means m sub L goes from -3 to +3, leading to 7 f orbitals. All of these orbitals can be available to hybridize. In this case, starting from the bottom, since it's AX4, I need 4 orbitals. That means I will take the 1s single s orbital and all 3 of the p's to give an sp3 hybrid. Observing other examples. Ammonia. Nitrogen is in group 5. There are 3 hydrogens, leading to ammonia having 8 valence electrons. Nitrogen can form 3 bonds to the 3 hydrogens. Those 3 bonds use up 6 of the electrons, leaving 2, which go to the nitrogen to complete the octet, giving NH3, again, a general form of AX3E1. We know that this is trigonal pyramidal. Also, because it has that lone pair of electrons, it is not perfectly symmetric, therefore it is polar. Once again, looking at the type, AX3E1, 3 plus 1 once again adds up to 4, so I need 4 orbitals, so I'll take the s and the 3 p's to make an sp3 hybrid on the nitrogen. Going further into hybridization and molecular orbitals. Again, atomic orbitals combine to form molecular orbitals. Your atomic orbitals in order, L equals 0 is an S, L equals 1 is a P, 2 is a D, and 3 is an F. When they combine to form molecular orbitals, the Latin alphabet is simply translated or transformed into the Greek. So for L equals 0, an S as a molecular orbital becomes the Greek letter for S, sigma. P becomes the Greek letter for P, pi. D becomes a delta. And F becomes the Greek letter for F, phi. In both cases, electrons still travel in pairs because the last quantum number spin only has a value of +0.5 or -0.5. There can only be 2 electrons in an atomic orbital or 2 electrons in a molecular orbital, which is why there's 2 electrons per bond. Also, each covalent bond contains exactly 1 sigma bond. You'll see in a second how, once again, the Lewis structures can easily determine not only the hybridization, but the number of sigma or pi or delta bonds that are present. Looking at the molecule CH2O. Draw the Lewis structure. Count the valence electrons. Carbon contributes 4, oxygen 6, each hydrogen gives 1, for a total of 12 electrons. For the skeleton, carbon forms the most bonds, and it has 3 things to bond to. So a single bond goes to the oxygen and each of the hydrogen. Those 3 bonds use up 6 electrons, leaving 6. As drawn, carbon needs 2, oxygen still needs 6 to get an octet, so I need 8 electrons, but I only have 6. Therefore, an additional bond is necessitated, leaving 4 electrons, which will go to the oxygen to complete the octet. This is the correct Lewis structure. What can it tell us? First of all, it tells us that this has a form of AX3, which means the molecule is trigonoplanar. Also, as it is not symmetric, the oxygen is not equal to the hydrogens, it is going to be polar. Since it is AX3, I need 3 orbitals, so now I will take an S, but I only need 2 more P's to add up to 3, so it's an sp3 hybrid. Finally, the original skeleton tells me 3 sigma bonds are present. That does not contain all of the possible bonds. So you will see that the double bond to the oxygen contains 1 sigma bond, and it also contains 1 pi bond. Another example, CO2. Again, carbon gives 4 electrons. Each oxygen gives 6 electrons, leading to a total of 16. Placing carbon in the middle with sigma bonds, now we know in the skeleton, 2 bonds accounts for 4 of the electrons, leaving 12. Each oxygen still needs 6 to make an octet, and the carbon needs 4. So although I only have 12 electrons left, I actually need 16. In order to make up the shortage, you share 4 more electrons, 2 more bonds. That leaves 8 electrons, 4 of which go to each of the oxygens to complete the octet. This molecule, with carbon being A and oxygen being X, has the general form of AX2, which means it's linear, it's symmetric, so it's nonpolar, and in this case, AX2 requires only 2 orbitals to hybridize, so there will be 1 S and 1 P to make an sp hybrid. 4 bonds, 2 double bonds are shown. Each double bond contains 1 sigma bond. So AX2 has to have 2 sigma bonds. The double bond itself is made of 1 sigma and 1 pi, so the 2 remaining bonds, carbon dioxide has 2 sigma bonds, 2 pi bonds, it's linear and nonpolar in an sp hybrid, and all of this can be seen from the Lewis structure. Finally, a molecule that was again shown before, SF6, where sulfur has 6 valence electrons. Each fluorine gives 7, for a total of 48 electrons in the molecule. As fluorine only forms 1 bond, you have 6 bonds formed, taking care of 12 of the electrons. Each of the 6 fluorines needs 6, taking care of the 36 remaining. You have a Lewis structure that you've already seen in previous videos as a form of AX6, which means it is octahedral. It is also nonpolar. In this case, I need 6 orbitals to hybridize. So that would be 1s plus the 3 p's plus the 2 d's for an sp3d2 hybrid. Also, AX6 means that there are 6 sigma bonds, one between each fluorine and the sulfur, and therefore, as those are all of the bonds, there are no pi bonds. So, in bonding, you can either exchange electrons in an ionic bond or share them in a covalent bond to form a molecule. You've seen that in sharing electrons, a Lewis structure is a very, very powerful tool that not only allows you to see what the molecule looks like, but it will also tell you its reactivity in terms of its polarity and its electronic structure in terms of hybridization and the number of sigma and pi bonds which are present. I hope you have found these videos somewhat useful and somewhat enjoyable, and thank you for listening.